Hello, my mathematical friends. Today we're going to prove this absolutely beautiful inequality here. And I'll tell you what the a's and b's and delta and the x is later on as we go along in the process. So what do we need to prove this inequality? Well, we need convex functions, very powerful tool, and the convex polygon stuff. I'll leave links to the videos in the description box. And we need some analytic geometry, which is an interesting addition to the mix. And then finally, we will need a whole lot of algebra, so we have to have patience. Let's return to the figure that I had in the last video, and let's examine this carefully. F of x is a function that's convex on the interval x1 to x2. So here's x1. And here is x2. And the function is guaranteed to be convex on the interval, but a lot of the functions that we've been using are convex everywhere. Then we choose k points along the x-axis. Here I actually chose, I have to choose a finite number of them. I chose 6 of them, so my k is 6, but in general it's k. And so we can make vertex points. For example, this vertex here, the x component is a3. Okay, and the y component is f of a3, like this, f of a3. So that's this y component. So we know the x and the y component of all of the vertices. Let's assume we have normalized weights. So here, the weight of vertex v1 is q1, the weight of vertex v2 is q2, and so on and so on. And these are normalized so that q1 plus q2 plus ... plus qk is... yes, you guessed it, it's 1, like that. So now it's easy to calculate G, the weighted mean of all these points. It's just the linear combination of the vertices. And this is a vector or a point, so it has an x component and a y component, gx and gy. Easy to separate them, just plug this in to all of these vertices here. Do the algebra, add it all up, and you can find gx, gy. We need that because this point here is the projection down from G, as I talked about before. And the x component here, s of x, we can find from G because s of x is g of x. If it's the perpendicular projection of this point G down onto the x-axis here, so s of x is g of x. And so it's really easy to get s of x. It's just the linear combination of the a's weighted by the q's. And I'm going to give this a short name. I'll call this x. It makes sense because this is the x-axis here, so this is x. And I'm interested now in thinking about the following. In fact, this kept me up at night for the last couple of days. What I was thinking about is this. We know that the following inequality, SP less than or equal to SG. So the length from point S, let me use some color, from point S all the way up to P, that's less than from S all the way up to G. We know that has to be true because pi here, the polygon pi, V1, V2, oh, I might as well write that down, hang on. Pi is the polygon made from all these vertices, so the centroid or weighted mean, okay, both of them have to be inside polygon pi. So, okay, that implies one thing, that SP has to be less than or equal to SG. But what kept me up at night, and I was thinking for a couple of days now, is that other question that I briefly mentioned in the last video. If we keep going with this line, well, I'm going to get another point up here, Q, and now SG has to be less than or equal to SQ. So, okay, this inequality here gave us Jensen, not Jansen, but Jensen, Jensen's inequality, but this is an extra one here. This now is less than or equal to SQ. See, Q is higher. And so what does this give us? This part. Well, this is not Jensen. This is going to give us something else. And this is quite interesting. I was wondering for a couple of days now, like, well, this must give rise to an interesting inequality. And indeed it does. Okay, and we'll see what it is. That's the whole point of this video. I want to answer this very interesting question. What does this do? We know that this part here gives us Jensen, but what about this part? This inequality here, these two are, this one is above G, you see? What's that going to give us? Well, we're going to see right now. Our first job is to find Q. And you'll notice that Q lies on a line. It's the line from vertices V1 to the last one, VK. And in terms of coordinates, it's A1, FA1, and AK, FAK. Now, if we look at this carefully, it's kind of interesting to notice that A1 is actually the minimum of all these A's, and A6 or AK is the max. So let me give some special names here. Big A is going to be the minimum of all of these A's, and we'll call the maximum big B. Now, I choose A and B because there will be too many indices in all of our algebra, and it will become difficult to see what we're doing. But if we make this simplification, it's better. And if you use your intuition, you'll see that this line here, well, you need to know the slope, so at some point you need to know delta x, right? So let's call that delta, and that's b minus a. So intuition tells us that whatever inequality we're going to have is going to depend on this delta b minus a, just because we know that this is a line. Now, you remember we said s of x, we call it little x. Okay, so our job here now is to find this y. So there's my x, and I need to find y, and this point here is xy. So given x, what is y? If we can find an equation for this line, so y equals mx plus b, if we can find this, then we're done. We know q for any g. G could be anywhere inside the convex polygon. We will be able to find the q that corresponds with that g. So now it's time for some analytic geometry. We must now find an equation for the line going through 2 points. So here are my 2 points, x1, y1, and x2, y2, and I want to find an equation for the line going through them. Well, I choose one of these points as something special. I'll choose this one. And so y minus y1 over x minus x1, I could have chosen the other one here, but I chose the first one. This has to be equal to the slope, which is easy to calculate, y2 minus y1 over x2 minus x1. Solving for y, I get this, and this is my equation of the line that I am going to use. Now, for our case, the first point here is a1 and f of a1. That's my point v1. And here, my point is vk, my last point. And those have coordinates ak and f of ak, like that. But if you recall, we wanted to make things a bit simpler to write. So a1 is big A and ak is big B. This is the minimum of the A's, and this is the max of the A's. So this is going to have coordinates big A, f of A, and this will have coordinates big B, f of B, like this. Plugging in the f of A's and B's and so on, I get this equation here, which I can do one more thing. F of B minus f of A over delta x minus A plus f of A. And there's the equation of our line, which we will use now. Well, this is a very interesting equation. So you might be wondering, well, what if I choose the other point? Well, that's going to be an exercise for you. So just for practice, choose, instead of y1 and x1 here, choose y2 and x2. Repeat all these calculations, and all the calculations I'm going to do below. It's actually fun to do. It's interesting, and you should do it. Okay, now we have to make a decision about using a convex function, and I will decide to use one of my favorite ones, minus log of x. That will be our convex function. So let's put this in here and compute the equation of the line. And we get this. But with the magic of logs, we can compress all this stuff together, and we get this. And the log applies, of course, to the whole thing here like that. And we can continue. We can compress this further. Log. We get that. And that's actually pretty good, but we might want to bring this into a more symmetrical form just to make it look prettier. So I'm going to examine this on its own. Let's see, I need some more room. Okay, I'm going to make some room. Hang on. I had to move that graph out of the way. All right, so we've got this. Let's look at this thing here. Okay. Oh, hang on. Let's get my pen. This thing. So 1 over a, then a over b to this big power. And let's separate these things out. Let's expand some of this. A x minus a over x minus, or this is actually b minus a here, and this is b x minus a, b minus a. That should be a power, so I should put this lower. All right, so multiplying this by 1 over a, I've got to subtract 1 from that thing. Okay, so let's do a side calculation. This, all right, this is, put everything on one denominator, x minus a minus b plus a over b minus a. And this, well, the a's go away, and I have ax minus b over delta. So I get this pretty formula. Look at this. X minus b over delta over b x minus a over delta. Now that's pretty. I mean, the symmetry of this is really beautiful. Okay, so now we can write down our log equation. I'll erase some of this stuff. Believe it or not, that's the equation of our line. Very good. So now let us go back to looking at the graph, that picture that we had in the beginning. Let's take stock of what we have done. We have now our equation of this line here. Okay, and we can actually make this just a wee bit easier to write. So I took the 1 over delta out of this fraction, this powers, I took it out. Now, let's think about this. Our x here, we have a special x, which if you recall, this is sx. This is q1 a1 plus dot 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 plus q k a k. So with this x, we now know q, we now know y. Y is equal to this expression here. Okay, so we know this, so we have figured it out. And now let's apply the inequality. Polygon pi is convex, therefore G is an L inside polygon pi. And that gives us the following very interesting inequality, that SG is less than or equal to SQ. Very interesting. So we have everything in place. It's time to figure out, what does this imply? Where does this go? What does this look like exactly? Well, okay. I have just enough room here. Hang on. This is good. Okay, so why is that? All right, so let's think about it. Up here, SQ, that is this value. That's that length. Okay. And SG, well, we know that that's the weighted mean, so I can now easily write this. Here's my weighted mean, and I put in my log function, so I have Q1 log A1 minus Q2 log A2, and so on, minus QK log AK. And as we did before in other previous video, we can compact all this stuff together. We get minus log of this big product. This is the generalized, kind of like generalized geometric mean. And so that new inequality here implies this. Let's have a look at it. Very beautiful. Let's get rid of the minus sign. I got rid of the minus sign. Well, when I take this right-hand side over to this side, left-hand side, there's going to be a minus here, but I took that minus inside by taking the reciprocal of this argument, so I flipped it upside down, and I get this now. Now let's get rid of the logs. Okay, very good. And I forgot my 1 over delta. Okay, let's put back, you see, put back that 1 over delta right here. Okay, we don't want to forget the 1 over delta. And there we have it. That is the inequality we wanted to prove. This could have been maybe a pretty good Olympiad problem, you know, and we did it by basic methods, geometry, convex things. But let's look at this. Let's write down the conditions under which this makes sense. Q1 plus Q2 plus, as you know, QK, they're normalized weights. And the X is the weighted mean of the A's. Plus Q2A2 plus dot 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 plus QK AK. And the A, of course, is minimum of the A's, and big B is maximum of the A's, and delta is B minus A. Now, I did some computer experiments with this, so I took, you know, random, well, the first one I took is like 1, 2, 3, 4, 5, 6. I took these weights, and then I constructed the Q's from these weights. All right, so you know how to do that. I showed you how to do that in the last vid. And I chose some A's, so I constructed Q's, and I chose A's, and then I did all these calculations to verify this, and it works. And it's very interesting, and you should do it as an exercise in computer programming, and also to get a feeling for how inequalities work. Well, this has been a really interesting exploration, and it resulted in this beautiful inequality, but I think we can do a bit more. First of all, let's notice that X has to be in between A and B, because A is the minimum and B is the maximum. And X is a convex combination of these A's, and all the A's are in between big A and big B. So, of course, it's like a centroid or a weighted mean, and it's going to be in the middle. So, in fact, X minus A is a positive number, but X minus B, that's negative. So we should take this denominator up to the top. That would be more logical. And we get this. Now, let's think about this. This here is like generalized geometric mean, but this is also generalized geometric mean. Why is that? Well, you see the generalized geometric mean, the powers Q1 plus Q2 plus so on have to add up to 1. But let's see what happens here. Is that the case? B minus A plus X minus A over B minus A, and that is indeed the case, B minus A over B minus A, and it's 1. So this here on the left-hand side is a generalized geometric mean. So the geometric mean of the minimum and the max is less than the geometric mean, you know, generalized geometric mean of any combination. If we use these powers. I mean, and I think this is really interesting. The symmetry of this is really interesting, and the two generalized geometric means on both sides. It's very, very beautiful. Here, let me write beautiful. It's so beautiful. Okay, that's so nice. And you're no doubt thinking, well, what would happen if I use f of x is x squared, and 1 over x, my other convex functions? Well, that's for you to explore. You go ahead and explore it. I haven't looked at this. Why don't you look at it and write about it in the comments? Well, that's it. We've come to the end. It's been a really interesting investigation, very exciting. And if you like this video, click like. And if you really like this video, well, click subscribe. And I will see you next time.